For most of human history, the night sky felt familiar. It stretched above ancient civilizations as a silent, unchanging dome, filled with stars that seemed fixed in place, repeating the same patterns night after night, year after year. To the people of ancient Mesopotamia, Egypt, Greece, China, and the Indus Valley, the stars were not distant suns. They were symbols, stories, gods. The sky was not a physical place, it was a mythological one. But even in those early observations, something didn't quite fit. A handful of stars didn't behave like the others. They moved, slowly but noticeably. These wandering lights were called planets, the Greek word for wanderers. Today, we know them as planets. This was the first crack in the illusion. The sky was not fixed. It was dynamic. For centuries, however, humanity held onto a powerful belief that everything revolved around Earth. This idea, known as the geocentric model, was formalized by the Greek astronomer Claudius Ptolemy in the 2nd century. In this model, Earth sat at the center of the universe. The sun, moon, planets, and stars orbited around it. The cosmos was finite, ordered, and designed for us. It was elegant, it was intuitive, and it was wrong. In 1543, a Polish mathematician and astronomer named Nicholas Copernicus proposed a radical alternative. He suggested that Earth is not the center. Instead, it orbits the sun. This heliocentric model simplified planetary motion and explained the strange behavior of the wandering stars. But it challenged more than astronomy. It challenged humanity's place in existence. At first, the idea was controversial. Galileo also observed the phases of Venus, something that could only be explained if Venus orbited the sun. The heliocentric model was no longer theoretical. It was observable. Humanity had taken its first step away from the center of the universe. But the scale of that universe was still misunderstood. For centuries after Galileo, astronomers believed that the entire universe consisted of a single vast structure, the Milky Way, a glowing band of stars stretching across the night sky. This galaxy was thought to be everything. All stars, all planets, all of existence. Beyond it, nothing. That belief would last until the early 20th century. In 1920, two astronomers, Harlow Shapley and Heber Curtis, engaged in a historic debate. It became known as the Great Debate. The question was simple: what are the spiral nebulae? Shapley believed they were part of the Milky Way. Curtis argued they were separate galaxies, island universes far beyond our own. At the time, there was no way to prove either side. Then, in 1923, everything changed. Using the 100-inch Hooker telescope at Mount Wilson Observatory, Edwin Hubble observed a star in the Andromeda Nebula. It wasn't just any star. It was a Cepheid variable, a type of star whose brightness changes in a predictable way. By measuring its brightness, Hubble calculated its distance. And the result was astonishing. It was far outside the Milky Way. The Andromeda Nebula was not a nebula. It was a galaxy. Today, we call it the Andromeda Galaxy. In that moment, the universe expanded overnight. From one galaxy to many, from one island to an ocean. But Hubble's discoveries didn't stop there. In 1929, he made another observation, one that would redefine reality itself. By studying the light from distant galaxies, Hubble noticed something remarkable. The light was shifted toward the red end of the spectrum. This redshift indicated that the galaxies were moving away from us. And not randomly. The farther a galaxy was, the faster it was receding. This became known as Hubble's law. The implication was profound. The universe is expanding. Space itself is stretching. And if you reverse that expansion, everything converges to a single point in the past. A beginning. This idea would later become known as the Big Bang. For the first time, humanity understood that the universe had a history, a beginning, an evolution. But even then, we had no idea how vast it truly was. That understanding would only come decades later, with the launch of a telescope that would change everything. In 1990, NASA launched the Hubble Space Telescope into low Earth orbit. It was one of the most ambitious scientific instruments ever built. Unlike ground-based telescopes, Hubble operated above Earth's atmosphere. This gave it a clear, unobstructed view of space. No atmospheric distortion. No weather interference. But the mission did not begin smoothly. Shortly after launch, scientists discovered a flaw in Hubble's primary mirror. Images were blurry. The telescope was effectively compromised. For a moment, it seemed like a failure. But in 1993, NASA astronauts performed a daring servicing mission. They installed corrective optics, essentially giving Hubble glasses. The results were extraordinary. Hubble began delivering images unlike anything humanity had ever seen. Towering pillars of gas in nebulae, galaxies colliding in cosmic dances, stars being born in glowing clouds. But its most important contribution was not beauty. It was scale. In 1995, astronomers pointed Hubble at a tiny, dark patch of sky, a region that appeared completely empty. They let it stare for 10 days. The result was the Hubble Deep Field. When the image was revealed, it shocked the world. That empty patch of sky contained thousands of galaxies, each one filled with billions of stars. And that patch, it was smaller than a grain of sand held at arm's length. This meant that the entire sky, every direction, was filled with galaxies. The universe was not sparsely populated. It was overwhelmingly dense with structure. Hubble didn't just show us space. It redefined it. Even with all its achievements, Hubble had limits. The earliest galaxies were too distant. Their light had traveled for billions of years. And because the universe expands, that light stretched into infrared wavelengths. Hubble wasn't optimized for infrared. To see deeper, we needed something new. That led to the creation of the most advanced telescope ever built, the James Webb Space Telescope. When the James Webb Space Telescope began its first deep-field observations in 2022, astronomers expected to refine existing models of galaxy formation. Instead, they encountered something unsettling. Galaxies that appeared too massive, too early, too structured. The standard model of cosmology predicts that after the Big Bang, matter slowly cooled, forming hydrogen clouds. Gravity gradually pulled these clouds together, forming the first stars, and later, galaxies. This process should take hundreds of millions of years. But Webb revealed galaxies already containing billions of stars less than 500 to 700 million years after the Big Bang. One of the researchers analyzing early data, Rohan Naidu, noted that some galaxies appeared far too massive for their cosmic age. These were not small proto-galaxies. They were structured, luminous systems resembling mature galaxies. Astronomers began calling them early massive galaxies, and informally, impossible galaxies. Not because they violate physics, but because they violate our timelines. If confirmed at scale, these findings suggest one of three possibilities. First, star formation in the early universe was far more efficient than expected. Second, galaxy formation began almost immediately after the first matter cooled. Third, and most radically, our understanding of cosmological evolution may be incomplete. Each explanation reshapes one conclusion. The universe became complex much faster than we thought. And if complexity arises early, then planets, and potentially life, may also have formed earlier than expected. On the largest scales, galaxies are not randomly scattered. They form a structure known as the cosmic web. This web consists of filaments of galaxies, dense clusters, vast empty voids. Galaxies are not isolated objects. They are nodes in a vast cosmic network. The existence of this structure was confirmed through large-scale surveys like the Sloan Digital Sky Survey. At its densest intersections lies massive galaxy clusters such as the Virgo cluster. The formation of this web is driven by gravity, but not just ordinary matter. It is shaped primarily by invisible mass. In 1933, astronomer Fritz Zwicky studied the Coma cluster and noticed something impossible. Galaxies within the cluster were moving so fast that, according to visible mass alone, the cluster should have flown apart. It did not. Something unseen was holding it together. He called it Dunkel Materie, dark matter. In the 1970s, Vera Rubin studied galaxy rotation curves and confirmed the same anomaly. Stars far from galactic centers were moving too fast to be explained by visible matter. The conclusion was unavoidable. Most of a galaxy's mass is invisible. Today, dark matter is estimated to make up about 27% of the universe. It does not emit light. It does not absorb light. It does not interact electromagnetically, yet its gravity shapes galaxies, clusters, and the cosmic web itself. Without it, galaxies like the Milky Way would not hold together. If dark matter binds the universe, dark energy pulls it apart. In 1998, two teams led by Saul Perlmutter and Adam Rees made a shocking discovery. They were studying type Ia supernovae, standard candles used to measure cosmic distance. They expected the universe's expansion to be slowing. Instead, it was accelerating. This meant a mysterious force was driving galaxies apart faster over time. We now call it dark energy. It accounts for roughly 68% of the universe. But its nature remains unknown. Maybe energy of space itself, property of vacuum, or a new fundamental field. Whatever it is, it determines the fate of the universe. The observable universe stretches about 93 billion light-years across. This does not mean the universe is 93 billion years old in size. It reflects cosmic expansion. Beyond this boundary lies a region we cannot observe because light has not had time or ability to reach us. There may be regions forever hidden from human observation, possibly infinite. This leads to a profound realization. Everything we know is everything we can see, not everything that exists. For decades, astronomers estimated about 100 to 200 billion galaxies. But in 2016, research led by Christopher Consolis revised this number dramatically. By analyzing deep field data and galaxy evolution models, the team concluded the observable universe may contain up to 2 trillion galaxies. Each galaxy contains hundreds of billions of stars, potential planetary systems, environments for chemistry and life. Even if only a small fraction support life, the number of potentially life-bearing worlds becomes astronomical. In 1961, astronomer Frank Drake created the Drake equation. It estimates intelligent civilizations based on star formation rate, planet frequency, habitability, life emergence, intelligence development. Even conservative estimates suggest life should exist beyond Earth, and yet we have found none. In 1950, physicist Enrico Fermi asked, "Where is everybody?" This became the Fermi paradox. If life is common, why is the universe silent? Possible answers: life is extremely rare. Intelligence is self-destructive. Civilizations are too far apart. Or we are not listening correctly. One explanation is the Great Filter. Some step in evolution is extremely unlikely. Origin of life, complex cells, intelligence, technology, survival. If the filter is behind us, we are rare survivors. If ahead of us, civilizations may inevitably collapse. In 1992, the first exoplanets were discovered. In 1995, a planet orbiting a sun-like star confirmed planetary systems beyond our own. Programs like SETI have scanned the skies for decades. In 1977, the WOW signal was detected, an unexplained radio burst lasting 72 seconds. Never repeated, never explained. We searched the universe using light, radio waves, infrared. But advanced civilizations may use technologies we cannot detect. We may be surrounded by signals we do not recognize. The universe will exist for trillions of years. We may be among the first intelligent civilizations to emerge. So, we are not late. We are early. Future telescopes will map exoplanet atmospheres, detect biosignatures, explore deeper cosmic history. We are entering the first true era of interstellar detection. Across trillions of galaxies, across billions of years, across unimaginable distances, we find silence, not because life is absent, but because the universe is vast beyond communication. We are one planet, one star system, one galaxy, among trillions. Yet we are also the first known point where the universe became aware of itself. Every telescope, every discovery, every question is the universe trying to understand itself. And so the question remains, are we alone, or just early? In the beginning, the universe was not light-filled. It was dark. After the Big Bang, the universe expanded rapidly in a hot, dense state. But for a long time, there were no stars, no galaxies, no planets. Only a glowing fog of hydrogen, helium, and radiation. This period is known as the cosmic dark ages. For hundreds of millions of years, photons could not travel freely. Space was opaque. Light was trapped inside a dense plasma. Then something changed. Gravity slowly began to win. Tiny fluctuations in density, quantum ripples from the earliest moments, began to grow. Slightly denser regions pulled in more matter. And over time, these regions collapsed into the first stars. These were not like modern stars. They were massive, unstable, and extremely hot. Astronomers call them population 3 stars. They contained almost no heavy elements. No carbon, no oxygen, no iron. Only hydrogen and helium, the simplest building blocks of the universe. These stars burned fast and died young. Some may have lived only a few million years before exploding as supernovae. But in their death, they created something essential. The first heavy elements in the universe. Without them, there would be no planets, no Earth, no life. As these first stars formed in clusters, gravity began shaping larger structures. Gas clouds collapsed into rotating systems. These systems slowly became the earliest galaxies. The transition from star clusters to galaxies was not smooth. It was chaotic, violent, explosive. Gas collided at enormous speeds. Supernovae reshaped entire regions of space. Black holes may have formed early, consuming surrounding matter and regulating galaxy growth. Modern simulations suggest that early galaxies grew through rapid mergers rather than slow evolution. Smaller structures collided and fused repeatedly. Each collision triggered new waves of star formation. This chaotic early universe laid the foundation for everything we see today, including the Milky Way. Our galaxy itself is the result of billions of years of mergers. It absorbed smaller galaxies, stretched them into streams, and built its spiral structure over time. We are not born from a single event. We are built from cosmic collisions. When the James Webb Space Telescope began deep field observations, scientists expected to see faint, small early galaxies. Instead, they saw surprisingly large and structured systems. Some of these galaxies appear as early as 300 to 500 million years after the Big Bang. This is extremely early in cosmic terms. Too early for traditional models to easily explain. Galaxies like Jade's GSZ 13-0 and similar candidates appear unexpectedly bright and massive. This suggests one of two possibilities. Star formation was extremely efficient in the early universe. Current galaxy formation models are incomplete. Either way, the universe is revealing itself to be more complex than expected. One key scientist involved in early JWST interpretation, Rohan Naidu, emphasized that these observations are still being refined. But the trend is clear. The early universe may have formed structure faster than predicted. This forces cosmologists to reconsider assumptions about dark matter behavior, gas cooling rates, early black hole formation, star formation efficiency. In cosmology, time is not just a measure, it is a structure. Early universe evolution follows strict physical constraints. Gravity pulls matter together. Radiation resists collapse. Expansion stretches space. The balance between these forces determines how quickly galaxies form. But JWST suggests this balance may have tilted earlier than expected. If galaxies formed faster, then black holes may have formed earlier. Heavy elements may have spread sooner. Planet formation may have started earlier. This opens a profound possibility. Life-supporting conditions could have emerged earlier in cosmic history than previously believed. The invisible structure holding early galaxies together is the dark matter. Dark matter does not interact with light, but it interacts with gravity. This means it formed the first gravitational scaffolding of the universe. Normal matter, hydrogen and helium, fell into dark matter wells. These wells became the seeds of galaxies. Without dark matter, galaxies would not form, stars would scatter, cosmic structure would dissolve. Dark matter is not just present in galaxies. It defines them, yet despite decades of research, we still do not know what it is. Candidates include weakly interacting massive particles, WIMPs, axions, modified gravity theories, but none have been confirmed. So one of the universe's most important components remains invisible and unknown. The discovery of cosmic expansion came from Edwin Hubble in 1929. But modern measurements reveal something even more surprising. The universe is not only expanding, it is accelerating. This was discovered in 1998 by studying distant supernovae. The expansion rate is increasing over time. This means something is pushing space apart. That something is called dark energy. Dark energy is not well understood. Maybe energy of empty space, a property of space-time, or something entirely unknown. What we do know, it dominates the universe. Roughly 68% of all cosmic energy is dark energy. This means most of the universe is not matter. It is not galaxies. It is not stars. It is a force acting on space itself. The observable universe has a limit. Beyond a certain distance, light has not had time to reach us. This boundary is called the cosmic horizon. It is not a physical wall. It is a limit of observation. As space expands, some regions move away faster than light can travel toward us. This means they will never be seen again, ever. Even with perfect technology, parts of the universe are permanently unreachable. This creates a paradox. The universe exists beyond what can ever be observed. Early estimates suggested around 100 billion galaxies. Later studies revised this upward, then again, and again. Now, using deep field extrapolation, scientists estimate up to 2 trillion galaxies may exist in the observable universe. This estimate comes from work led by Christopher Consulis. Most of these galaxies are small, faint, and difficult to detect. Many are dwarf galaxies, but even small galaxies contain millions or billions of stars. The scale becomes incomprehensible quickly. If each galaxy contains 100 billion stars, and each star has planets, then the number of worlds becomes almost unimaginable. With modern exoplanet discoveries, we now know that planets are common. Most stars likely have planetary systems. Some of these planets are rocky, Earth-sized, located in habitable zones. The universe may contain billions of potentially habitable worlds. But habitability does not guarantee life. It only creates possibility. Despite trillions of planets, despite billions of years, despite countless opportunities, we have not detected confirmed extraterrestrial life. This brings us back to the Fermi paradox. If life is common, why is the universe silent? Possible explanations. Life is rare. Intelligent life is unstable. Civilizations self-destruct, or they are too far apart to communicate. The answer remains unknown. As telescopes improved, humanity began shifting focus from galaxies to individual stars, and then to the planets orbiting them. The discovery of exoplanets changed everything. Before 1992, we had no confirmed planets outside our solar system. Today, we know of thousands, and statistically, billions more likely exist in the Milky Way alone. Many of these worlds orbit within the so-called habitable zone, the region around a star where temperatures allow liquid water to exist. Liquid water is not life itself, but on Earth it was the foundation of life. This is why missions like the James Webb Space Telescope are so important. They don't just detect planets. They analyze atmospheres. Webb can detect water vapor, carbon dioxide, methane, temperature signatures, These are called biosignatures, chemical hints that life might exist. But detection is difficult, because even if life exists, it may not resemble anything we know. On Earth, life is carbon-based. It depends on water, oxygen cycles, organic chemistry, but the universe does not have to follow Earth's template. Astrobiologists consider alternative possibilities: silicon-based life, methane-based organisms, subsurface ocean ecosystems, life in extreme radiation environments. Moons like Europa and Enceladus may contain subsurface oceans beneath ice layers. These hidden oceans are protected from space radiation. They may represent some of the most promising locations for life in our solar system. Even Mars shows evidence of ancient rivers and lakes, a planet that may once have been habitable. If life existed there, even microbial, it would prove that life is not unique to Earth. Even if microbial life is common, intelligent life is another question entirely. On Earth, it took billions of years for intelligence to evolve. And even then, it happened only once. This raises a difficult question. Is intelligence rare in the universe? Or does it simply not survive long? This leads to one of the most important ideas in modern cosmology: the Great Filter. The Great Filter suggests that somewhere between simple chemistry and interstellar civilization, there is a step that is extremely unlikely, or extremely dangerous. Possible filter stages include origin of life, complex cells, multicellular organisms, intelligence, technological civilization, long-term survival. We do not know where the filter lies. The uncertainty is what makes it unsettling. If the filter is behind us, we are rare survivors. If it is ahead, civilizations may tend to destroy themselves before reaching the stars. The universe is extremely old, about 13.8 billion years. That is enough time for civilizations to rise, spread, colonize galaxies. Yet we see no evidence of large-scale alien engineering, no clear signals, no confirmed contact. This is known as the Fermi paradox. The paradox becomes sharper with every new discovery, because the more planets we find, the more likely life should be, and yet the silence remains. One possible explanation is timing. We may be early or late, but not aligned. Civilizations may rise and fall at different epochs, separated not by distance, but by time. Even if intelligent life is common, two civilizations must exist simultaneously within communication range. That window may be extremely small. If humanity survives long enough, it will leave Earth, not as fiction, as necessity. The sun will gradually brighten over billions of years. Eventually, Earth will become uninhabitable. This is not speculation. It is astrophysical certainty. So survival requires expansion. The nearest star system, Alpha Centauri, is 4.37 light-years away. Even at our fastest spacecraft speeds, it would take thousands of years to reach. But future technologies may change this. Nuclear propulsion, fusion drives, light sails, relativistic travel concepts. Humanity's future may not be tied to one planet, or even one star system. The universe will not remain as it is. It is evolving toward a colder, darker state. As dark energy continues expanding space, galaxies will drift apart. Eventually, new star formation will slow. Existing stars will die. Black holes will dominate. This is called the heat-death scenario. A universe filled with darkness, low energy, isolated remnants. But this will occur trillions of years in the future, far beyond human timescales. There is a profound idea in cosmology. The universe is not just something we observe. It is something that requires observers. Without conscious beings, no one measures light, no one interprets data, no one asks questions. In this sense, intelligence gives the universe meaning. We are not just inside the universe. We are the universe becoming aware of itself. From Earth, to solar system, to galaxy, to cosmic web, to observable universe. Each step reveals a larger structure. and each step reduces our sense of centrality. We are not at the center. We are not even special in location. We are simply located at one point in an enormous structure. After all discoveries, after all telescopes, after all calculations, one question remains. Are we alone? We do not know, but we are no longer guessing blindly. We are searching with instruments capable of seeing across billions of years. If we imagine the entire history of the universe as a timeline, humanity appears at the very end of a long chain of events. Stars had to form. Galaxies had to evolve. Elements had to be forged. Planets had to stabilize. Life had to emerge. And then, we appeared. Every telescope pointing outward is also a mirror, because what we see in the universe is a reflection of our ability to understand it. The universe is not silent. It is just very large, very old, very complex, and we are still learning how to listen. We are not just observing the universe. We are part of it. And one day, we may understand it well enough to know whether we are alone or simply early. If this journey changed how you see the universe, make sure to subscribe and stay with us for more deep space discoveries. Because out there, among trillions of galaxies, the next answer could change everything.